Suppose, see, this is the expression for what? The divergence of the generalized vector. Okay. So you can write the divergence for, curl for any vector del cross A. The del cross A. Okay. Where A can be given by what? Where A is equals to AU plus AB plus AW. Okay, if the vector is given like this in any coordinate system, you have to write 1 divided by H1, H2, H3. This is H1 AU, H2 AV, H3 AW. Dou by dou U, dou by dou V, dou by dou W. H1 AU, you have to write the scalars. Okay, H2 AV, H3 AW. So like this. Okay, suppose if any vector is given is equals to 2x plus 5, 2x AX plus 5 YZ AY plus 3XZ AZ. So how can you find the del cross? Del cross A. Del cross A can be calculated by, here we have written AX, AY and AZ, dou by dou X, dou by dou Y and dou by dou Z. You have to write this 2x, what? 5 YZ, here 3 XZ, right? In the similar way, if you take any generalized vector in any coordinate system, okay, you have to write, instead of AX, AY, AZ, I have to write AU, AV, AW with the scaling factors. Okay, dou by dou U, dou by dou Y, dou by dou W. Here we have to write the scalar quantities. Okay, the components in X, Y, Z directions. The components in AU, AV, AW directions. So like this. Okay. So like this, you have to remember these generalized formulas, and they help very well. Okay. So now, till now we have seen how to calculate the flux leaving any surface. Okay. Leaving a closed surface or open surface, the expression is same instead of the open and closed intervals. Okay. If you observe, see, till now we have seen the Gauss law. Okay. Now, what are the applications of the Gauss law? What are the applications of the Gauss law? See, for calculating the electric field intensity, electric flux density, okay, or otherwise the force equations or the force between the 2 points. So it is better for you to apply what? The Gauss law. And Gauss law helps, simply you can find the what are the required electric field intensity or electric flux density. So by using the Gauss law, we can simply find the electric field intensity or electric flux density, okay, or the potential at any point also by using that. Okay. So like this, if you observe this, so till now I didn't tell you how to find the electric field intensity. Okay. Till now I didn't told you how to find the electric field intensity and how to find the electric flux density or magnetic field intensity or magnetic flux density. Just we have given you the just basics. Okay. So now the first one is application of the Gauss law. Okay. What is the first application? Applications of Gauss law. Application 1. The application 1 saying that is the E field, electric field intensity, due to a point charge. So how to find the electric field intensity due to a point charge Q? Okay, so we have to find the electric field intensity due to the point charge Q. Okay, so you have to know that. So suppose if you take any point charge Q, okay, if you take any point charge Q, you know that the electric flux will be radially outward from the Q. Okay, the field will be radially outward from the, we know this. Okay, suppose if you want to find the electric field intensity or electric flux density DRE anywhere in this field, already we know this is called as what? It is E field. Okay, suppose if you want to find electric field intensity or electric flux density at any point from the charge, let us suppose if I want to find the electric field intensity at this point P, what we have to do? I have to, because see, it is drawn in the 2D plane, but if you take any point charge in the space, the electric field will be like this. Understand? Like this. It will be, electric field will be in radially outward. It will be in all directions. Understand? So that means you can at a point, at a distance, here the point is presenting, so you have to find the electric field intensity due to this Q here. Okay, already we know the electric field will be generated, so how much strength will be presenting here we have to find. That is the question. Okay, so for this, what is this? I consider one closed surface here. I consider a closed surface. That means it is not a simple circle, it is just what? Sphere. I consider this closed surface. Okay, it is a closed surface. It is a closed surface. Okay, it is a closed surface. It is also called as the Gaussian surface, because I am applying the Gauss law. So I consider a closed surface around the charge. That closed surface around the charge is called as the Gaussian surface. So I am considering this surface. Okay, so now I have to apply the Gauss law to find this electric field intensity. Okay, see, what is Gauss law? The closed surface integral d dot ds is equals to the charge enclosed in the volume. The net flux leaving, what is this term saying? The net flux leaving any closed surface. Why it is net flux leaving? Coulomb per meter square into meter square is coulombs, means electric field, electric flux leaving any closed surface equals to the charge enclosed in the volume. Understand? Now let us suppose, what is this? I consider this Gaussian surface at a distance of r, right? At a distance of r. So this is a sphere of r now, radius r now. Okay, because it is r means it is an r constant surface. It is an r constant surface. You know, for r constant surface, what is the direction of this ds? ds will be ar only. ds will be in direction of what? ds will be in the direction of ar. Understand? ds will be in the direction of ar. Now see, observe this. This is closed integral d dot ds. See, on this r you will find the same strength here. Understand? Because these all points are equidistant from the cause charge. Okay, so that's why d is constant everywhere on the sphere we have considered. Okay, so that's why this is, you can write this one outside. You can write this one outside because it is constant. Because what? As R is equals to constant, what happens? D is also constant. You have to note this. As R constant, D is also constant. Okay. So that means you can write D outside. You can write this D into closed integral D dot ds. And it will be what? Q. Okay. This is ds. Understand? So now D into what is the surface area? See, integral ds. Integral ds is what? ds means the surface area. The surface area of this closed surface. So what is the surface? It is a spherical surface. You have to note that. It is what? A closed, it is a spherical surface. Symmetrical surface. I consider a symmetrical surface around this. Okay. There may be non-symmetrical surfaces also. Okay. There will be. So this will be, what is the symmetrical surface? For this symmetrical surface, what is the ds? See, it is the spherical surface. For the spherical surface, it is a sphere of radius of what? R. Then what is the surface area of the, we know, what is this? Integral ds is S is equals to Q. So from now, what I can write? D is equals to Q divided by S is nothing but the surface area. S. The surface area is what? 4 pi r square. Okay? 4 pi r square. The area of the sphere is 4 pi r square. Understand? I can write this S here. It is 4 pi r square. Now what is this? Electric flux density. We know the electric flux density is the vector. Okay? Then this is the electric flux density is nothing but the electric field only. Okay? So in which direction it is existing? In which direction it is existing? It is radially outward. Means it is in AR direction. Okay? So Q divided by 4 pi r square. Q divided by 4 pi r square. What are the units? Coulomb per meter square. So here you will get the field strength. Here you will get the field strength what? Q divided, whatever the Q is there, due to this Q, you will get the field strength here as Q divided by 4 pi r square. Coulomb per meter square. So this is the electric flux density due to the point charge at a distance r. Okay? So if you take any point charge Q at a distance of r, you can find the electric flux density as this Q divided by the surface area of the sphere on which the point of interest is present. Okay? So like this. So this is the electric flux density. So from this, can we find the electric field intensity? Not yet we find the electric field intensity. First what we calculated? The electric flux density. Then come to the Coulomb's law now. What the Coulomb has did that? The Coulomb has given the force measure. What is that? The force is equals to E into Q. Okay? He has defined the force between the two charges. Okay? In the electric field. Okay? So observe this, the force between the two charges. So from this, what can I write? I can write the electric field intensity as what? The force divided by the charge. The force per unit charge is called as the electric field intensity. This is called as what? The force per charge. The force per unit charge is E field intensity. What is saying? If it is taken as 1, the force is nothing but the electric field intensity only. Okay? So this, like this, he has taken. Okay? So now this is E equals to F by Q. And also, and he equated this with a d by epsilon. Because electric field intensity we know D is equals to epsilon E. Okay, and we can write that D can be written as, because why I am writing this D? Because already I found this D, right? So that's why I can use this. So from this, what I can write? So E can be written as E is equals to Q divided, what is D? D is equals to Q divided by 4 pi R square by epsilon. You will get what? E is equals to Q divided by 4 pi epsilon R square. What is the direction? The electric field direction is AR. The vector, the unit vector is very important. So it shows, what is this AR shows? The electric field is radially outward. It shows the meaning at what? Radially outward. So this is very important formula, and this is very important. At any point, due to a point charge, you can find the electric field intensity of what? Q divided by 4 pi epsilon R square. Okay, if the point charge is given at any place, if you want to find the electric field intensity, you have to apply this expression. Okay, so what are the units of this? The units are what? We know already, volts per meter. The units. So can we write one more unit for this? See, observe this. The electric field is defined as what? According to Coulomb, force per unit charge. For the force per unit charge, what can I write? I can write from this, what can I write? Force is Newton per Coulomb. Right? Force or Newtons, Q is Coulombs. So I can also write, or what can I write? Newtons per Coulomb. And this is very important unit. Okay, Newton per Coulombs are also the units of the electric field intensity. Here you have to notice, what is the electric field intensity? Force per unit charge. It is also called as force per the basic cause of the electric field. Okay, so like this, understand? So this is how to find the electric field intensity due to the point charge, anywhere. Okay, so now, so this is the electric field we got. Somewhere we find the electric field intensity E here. Okay, now observe this. Okay, so this is the electric field intensity. Now, suppose if I place one charge, if I place one more test charge here. Suppose if I place one more test charge into this field. Suppose if I take one test charge, some QT, I place into this electric field. Okay, what happens? Already you know these are electric flux lines, so definitely it will exert some force on this QT. Definitely it will exert some force. Okay, suppose if you take a same kind of charge, it will repel. If you take other kind of charge, it will attract, but definitely it will exert some force. Okay, that force is defined as what? F by Q. Okay, so that means what can I write? What is F by Q? The electric field intensity, the force can be written as what? The electric field intensity, already we know, this is force exerted on this QT, can be written as what? The force exerted on this QT can be written as the electric field intensity, already we find E into the QT, right? The force on this Q. Now Now what happens? Suppose already we have seen what is electric field intensity at this place. See what we have to find. The force on this QT due to this means the force on this QT is calculated as the force F is equals to E on this point Q and T, QT. Okay. So what is the electric field at here? Due to this is Q divided by 4 pi epsilon R square. What is this? You have to write the QT. So from this, what can I write? The force is equals to Q1, and also you have to write the AR also. Unit vector. QT divided by 4 pi epsilon R square AR. Okay. I can also write, suppose it is Q1 or Q2. Q1 or Q2. Okay. How can I write? The force can be is equals to Q1 and Q2 divided by 4 pi epsilon. The 4 pi epsilon R square AR. What is this AR? AR is from the point to this point. This is AR direction. Okay? This is AR direction. Suppose the coordinates of these points are given as X, Y, Z. The coordinates of this point is X1, Y1, Z1. Okay. Now how the AR can be written? AR is a unit vector, right? So it can be written as what? The vector from here to here can be written as x1 final minus initial. Okay, you have to write final minus initial. The vector representation is like this. So final minus initial is what? The force on QT due to this is equals to, this is x1 minus x into ax, okay, plus y1 minus y. This is x, y, z. This is x1, y1, z1. y1 minus y into ay plus z1 minus z into az. So this is the vector directed from here to here. But what is the unit vector? I have to divide this with the magnitude of this. What is the magnitude of this vector? x1 minus x square plus y1 minus y whole square plus z1 minus z whole square. So this is, understand? So this is the radial vector. So like this, if any point, see already we have find the vector, okay. So this is nothing but what? It is the distance between these two. Understand? What is this? R. R is equals to this one, distance. The denominator part is this, denominator part is R. Okay. So we can directly write QT divided by Q1 QT divided by 4 pi epsilon. Already we know this value. R is nothing but this value. Okay. AR, you have to write AR. AR is nothing but this one. Entire portion you have to write. So generally this force is a vector. Okay. Like this you have to identify. So you have to notice due to what charge, due to which charge, on which charge the force is exerting. Suppose if I want to find the force on this charge due to this QT, understand? If I want to find the force on this Q due to this QT, what I have to do? I have to take the direction from here to here. Okay? If I want to find the force on Q due to this QT, okay, the force must be in this direction. So this will be the final point and this will be the initial point. Now the direction changes. Right? The direction changes. So that is the thing you have to notice. Okay? On which charge representing the final point, due to which charge representing the initial charge. This is very important. Okay, you may take the wrong notation also. Okay, on which charge is the final point, due to which charge is the initial point. Okay, so this is the way you have to approach. So mostly I am covering where the people may get confusion. Okay, whether you have to take this one minus this one or this one minus this one. From now onwards there is no confusion. Okay. So here what we have taken? We have taken the Gauss law. By using Gauss law, we have taken the electric flux density and electric field intensity, and also we covered the Coulomb's law also. What is this law? What is this? This thing. This thing is called as the Coulomb's law. Okay. What are the units for this? These are the newtons, right? It is called as the Coulomb's law. So now what we have taken? Just we observed what? The electric field intensity due to the point charge, right? It is the application of Gauss law 1. Okay. Now suppose come to the magnetic fields. Okay. So come to the magnetic fields. So the total analysis will be different here. Okay. But we will use the results whatever we got in the electric fields there. By comparing the electric fields, we can get the results of the magnetic fields also. Okay, so that's why the comparison is very important, and it is very easy for you to analyze the subject. Okay, so now the next topic is Biot-Savart Law. What this Biot-Savart Law is saying, that is, suppose if we take any small length current carrying wire. Small length current carrying wire is nothing but what? It's a point current element. Okay. If we take any point current element, if we take any point current element, the point current element can be written as what? Suppose if this is the point current element is this much length, but I cannot write this much length as the figure, so that's why I am taking this much length. Okay, I am taking this much length. So on this length, just I have taken only this amount of length. So here the length is dl bar. Okay, let us suppose the current is flowing in this direction. Point current element means what? A very infinitesimally small length current carrying wire. Okay, you can also remove this. So due to this, what can we expect? So why I have chosen this concept here? The previous we have discussed the electric field intensity due to the point charge. Okay, the analogous to the point charge in the magnetic field will be the point current element. Okay, so that's why I have taken this. Okay, so due to the point charge already we find, due to the point charge we find the electric field intensity D. First of all, what we have calculated? We have calculated D is equals to Q divided by 4 pi R square AR, and we have found the electric field intensity as what? Q divided by 4 pi epsilon R square AR. The epsilon term is presenting here. Understand? So it is due to the point charge. The point charge. The point charge is nothing but, it is what? It is the basic cause. It is the basic cause of the electric field, right? The point charge. So now I have taken the small current element which is similar to that, but it is a current carrying element, that is a point stationary charge. Okay, so due to this, if I want to find at any point P, due to this, if I want to find the magnetic field intensity H, okay, from here to here at a distance of R, okay, how can we express the magnetic field intensity H due to this point current element can be written as at a distance of R, what? See, first of all, I am defining H here. From the Gauss law, what I have defined first? First of all, I have calculated D. Here I have to calculate H. Okay, and there also one similarity. Okay, while writing the what is that called? The outflow and divergence. Okay, while writing the outflow and divergence, or from the Gauss law, while writing the Gauss law, what I have taken? The strength term. The strength is equals to cos divided by the area, right? In the Gauss law. Okay. Suppose if you come to this, in the magnetic fields, in the circulation definition, okay, then what is the strength? Strength is equals to cos divided by the length. There we got the magnetic field intensity. So that's why the first strength term, already we said this one has the strength, this is also strength. Okay, for similarity, that's what I'm saying. Okay, I'm saying this. So H is equals to what? H can be written as, Q divided by C, that is Q divided by 4 pi R square. So Q divided by 4 pi R square means what? Basic cos divided by 4 pi R square into AR. So what is the basic cos here? This is the basic cos for the magnetic fields. It is the basic cos for the magnetic field. It is the basic cos for the electric field. So that's why H can be written as what? IDL. See, observe this. What is the basic cos there? The basic cos there is Q divided by 4 pi R square. I will also write what is the basic cos here. The basic cos here is point current element. What is the point current element can be represented? The point current element can be represented IDL bar. This is IDL bar, right? Where DL tends to 0. Okay? So the point current element is represented like this. Okay? So this will be is equals to IDL. IDL divided by 4 pi R square. This is similar to this. Because this is the basic cos. Here it is the basic cos. It is 4 pi R square. 4 pi R square, 4 pi R square. I have to write AR here. AR means radially outward vector. Here also I have to write radially outward vector. But it is just multiplication. But here you have to write that is AR. AR means the dot. Here the dot product here, right? So that means what? Here you have to take the cross product. It is the not simply into, it is the cross. So this is called as H field due to the point current element at a distance of R. The basic cos divided by 4 pi R square into AR. Here not, this is into, it is a cross product. Because it is a vector, so that's why it is a cross product. If you observe this entire one is a scalar and it is a vector. Okay, this entire portion is a scalar quantity. Q is a scalar quantity. 4 pi epsilon is scalar quantity. R is also scalar quantity. R is nothing but the distance between these two points from the charge to the point. Understand? So that's why. So this is the thing. So this is called as H is equals to IDL cross AR divided by 4 pi R square. And some people will write this one as DH also. Or some people will write H also. Okay, you can also write this DH. DH is nothing but the what? The electric magnetic field intensity due to the point current element. Okay, you can also write this one as DH. So because of the small current carrying length, current carrying element, I am getting the infinitesimally small magnetic field here. Understand? So this is called as the Biot-Savart Law. But we know what is B. B can be written as mu into H. So I can write mu is what? Mu ideal bar cross divided by AR divided by 4 pi R square. So this is called as the, what are the units of this? Ampere per meter. What are the units of this? Weber per meter square. So this is the magnetic flux density. This is the magnetic field intensity. Magnetic flux density are the units. For the magnetic flux density, these are the units, Weber per meter square. For the magnetic field intensity, ampere per meter are the units. Okay, the units are very important. And also, see, this is the magnetic field intensity. So from this, and the magnetic field intensity, just like that, how the Coulomb has expressed electric field intensity, the force per the basic cause. Okay, here also he expressed the force per the basic cause, right? Force per the basic cause, F by Q. Similarly, what can I write? Phase per the basic cause. Okay, I can write this or QT. Okay, so now similarly, what can I write? I can write the, see, in this, the first we obtained. Here, the first term we obtained. Next we obtained this one. Next we obtained this one. Understand? So I equated the next obtained term with the force per the basic cause. I have to equate the next obtained term B with the force per the basic cause. Okay, so what? The Lorentz. From the Lorentz law, from the Lorentz law, the B is expressed as the force per the basic cause. Okay, what is the basic cause here? The basic cause here is IDL. Here it is DF. Let us suppose we can write DF. The force per, or you can also write F divided by IDL. Okay. See, here the magnetic flux density is represented as DF divided by IDL. Here the electric field intensity divided by represented as F by Q. Force per basic cause, force per the basic cause. Okay, this is from the Lorentz. Lorentz law. Okay. So from this, what can I write? So DF is equals to what? DF is equals to IDL into B. It is a vector, it is a vector. I am writing this I as dq by dt. I am writing this I as dq by dt. This is dl into B. Okay. So because this is a vector and a vector, I cannot simply write this is like this, but I can write a cross product. So from this, what is df? Df can be written as, take this dq out, dl by dt cross B. So from this, what can I write? I can write F is equals to Q into what? Q into dl by dt. Here dl by dt is called as the drift velocity. It is the drift velocity or velocity. Velocity of the charged particle in the magnetic field. Okay, the velocity of the charged particle in the magnetic field. Okay, so from this I can write Q into F is equals to Q into dl by dt. This is dl by dt can be written as the velocity V cross B. And this is a very, very important relation. And this relation is called as the Lorentz law. the Lorentz force law. This is the Lorentz force law. And this is called as what? This is called as Lorentz force law of magnetic fields. It is the Lorentz force law of the magnetic fields. Okay, he equated the magnetic flux density with this. Okay, it is the force equation from the Lorentz law for the magnetic fields. Okay, he has described the nature of the fields in the electric field and also the the electric fields and the magnetic fields. Okay, so from this, what is the force? We got two kinds of force here. One is the electric force and one is the magnetic force. Okay, one is the electric force and the magnetic force. Okay, the total force is given as the total force is equals to electric force, the force of the charge particle in the force on the charge particle in the electric field and the force on the charge particle in the magnetic field. It can be written as, it is Q into what? Q into E plus Q into what? V cross B. This is, so I can write Q into, it is E plus V cross B. And this is a very, very important relation. Okay. Okay. It is called as Lorentz force equation. It is a Lorentz force equation. Okay. So this represents what? The nature of the field. Okay. So like this. Okay. I hope you got this. Okay. So that is what? Biot-Savart law. And what is the force in the electric field and what is the force in the magnetic field. Okay.